All right. So here's what I have in my first step. Does that look correct? Derivative of the top, 24x squared, ln x left alone, minus the top left alone, times derivative of the bottom, which is 1 over x, all over the bottom squared. Anything we can do there? Right there, that's what? That is 8x squared. That 1 over x does not multiply to this over here. That 1 over x does not cancel anything with that x. What you have is one term here and another term here that are separated by a subtract sign. So this is kind of its own thing, and this is kind of its own thing. So what I told the other class is you could stop right here with this. Now, a couple of things. Could you go farther? There are some things you could do. I'm not sure how much those help. Brittany, what's one? Okay, Sam? I could take this over that minus this over that. Now, when I did that, in the first fraction, it could cancel an ln x, right? The second fraction, there wouldn't be anything that would cancel. That's why I can't cancel this ln x with this ln x because it's not a factor of this one up here. But if I split it apart, which is legal to do in a fraction, then I could do that. Okay? And so that would be one thing.
You could factor out an 8x squared.
I could take out an 8x squared. And that would be perfectly fine if you did. However, there isn't anything down here to cancel with, right? Normally, the reason I factor something is like the e to the x up here earlier, so I could then cancel it out. So you could take out an 8x squared up on top, nothing to do with it when you get there, so I would say don't do it. But if you do it, I wouldn't count it wrong. So this is one, and again, you don't have to try to read my mind. It's like on the AP test. When we do problems that have units in it, a lot of times on the AP test, they give you a point for just having the right units. So, you know, if you're working the problem and you're not sure where to go, get at least something down and put units on it. You might get a point, right? But then on some other problems, they don't. It's like they run out of points. Every free response problem is like 9 points. And so if they've already allocated 9 points down to the answer, then a lot of times they won't give a point for the units. But sometimes they do. Well, my way of thinking is just always put units on there. And in case they give a point for that, then you got it. Then you're covered. So you don't have to try to read their mind whether they're going to give you a point for the units or not. Kind of the same thing here. You don't have to think, oh, should I do this? I mean, I guess there's part of you that is doing that. But if you see something you could do and it's legal mathematically, you know, what the heck? Go ahead and do it. You know, take out that 8x squared. Am I going to punish you for doing something correct, even though I'm just not requiring you to do it on that problem? Okay? So splitting it apart, I think, would be good. Now, why am I not requiring that? Why don't I think that's a big deal? Well, one of the big things we use derivative for, when we get to chapter 4 especially, is we want to set it equal to 0. Well, splitting that apart, now you've got two terms equal 0. I always think it's easier to solve if it's in one fraction, right? Because when is a fraction ever equal 0? When the top is 0, right? So I think to set this equal to 0 would be better in this form than what Sam suggested where we split it apart. So if we split it apart, yes, it would allow us to cancel an ln x, so that might look a little nicer. But if we were setting this equal to 0 solving, we'd be better off leaving it here. And then say, okay, now set the top equal to 0 and then go from there. So that's one of the reasons I don't get too caught up in reducing from there. All right, so that's kind of a nice one to practice there. All right, while we're on this idea of canceling and stuff, I got another one. I promise we'll let you ask some questions on 195. So let's do sine 5x over 4 to the x. There's your y right there. put up the first step here if you don't want to look. Don't look yet. And that might be it. I don't know. I'm just saying that's what I got. That's what I got with the first thing I did. Now that one on the bottom kind of reminds me of something here. When you see e to the x squared, and I never like it in the book when they write it like that, without parentheses, because I think it makes it a little confusing. This is that right there, okay? Now that's different than e to the x squared, right? Tell me how those two are different.
The second one,
As far as derivative would be a change, yeah.
the second one you could simplify to e to the x.
That's right. When you have a power on a power, you multiply the power. So e to the x squared is e to the 2x. Why is that? Well, it's because you have e to the x times e to the x, and you would add the powers. You would x plus x is 2x. So that's e to the 2x, where this is e to the x squared. So they're very different things.
So another way, I guess, is the one on the right would be like saying e to the x plus x, while the other one is e to the x times x.
That's right. This would be the same as, yeah, just writing it looking like that. Whereas this is e to the x times x. That's right. So they're two different things. All right? So back to this part then, power on a power. Because that's what I have down on the bottom, right? So 4, because somebody said this in the other class, somebody asked if this would be true. So 4 to the x is the same as 4 to the 2x, right? And wouldn't that be the same as 4 squared to the x? Wouldn't 4 to the x squared be the same as, right? I mean, an easy way to look at that is if you had 2 to the third to the second, that's 2 times 2 times 2, and then you got that twice. So that's 6 2s. Well, the other way to look at that is 2 squared to the third. Well, that's 2 2s 3 times, right? Either way, you got 6 2s multiplied together, right? So this would be 16 to the x, but the question is, would you want to write it that way on this one? And I don't think you would. But it would be okay, but I don't think you would want to write it that way. Okay, so is there more I can do?
Factor out a
4 to the x. Now that happens a lot with quotient rule that involves e to the x or 4 to the x or 2 to the x or something like that, because it's its own derivative. So when you take turns on your derivatives, when you leave it alone and when you actually do the derivative, you end up with the same thing. So both terms end up with a 4 to the x, because here we left it alone. Here when we did the derivative, it showed up again. So you end up getting it in both parts, which you can factor out and then cancel with one of those that's down there. So in the end, when it's all said and done, and I just realized that thing I wrote on the board, they couldn't see while I was recording, but anyway. So this 4 to the x and this 4 to the x, I could factor out of the top and cancel with one of these down here. And so it would end up looking like that. That is some simplifying I think you should do. Okay, to me that's fairly obvious, factoring out, and then it'll cancel, and we could do that. So those were a couple that we ran into second block that I wanted to make sure you saw.
So this was a multiplication problem. There's nothing on the bottom. That's what we still want us to take this for.
I would say not, but it wouldn't be wrong. Let me use a simple comparison of that. Let's say your final answer is 3x plus 6. Is it wrong to take out a 3 and write it 3x plus 2? No, but not necessarily. Because taking out the 3 didn't then allow me to do anything. I wasn't able to cancel it with something, so I wouldn't. So either one of those would be fine. Is that kind of what you were saying?
Yeah.
Okay. Yes. I think that's a fairly good way to say that. As we go through some more examples, I think we'll get to see some examples of those two things. Okay. Anything on 195 that you've tried and just couldn't get to match with maybe the back? Because really, if you eliminate 40, most of those are not quite as bad as 40. Most of them, and to be honest, most of them are in the medium It's a hard range. I mean, just because they have a product rule with a chain rule inside of it, you know, I mean, really, those ones on page 195, there's a few of them I would probably categorize as easy. But, 13. W cubed cosine 4W. I'm going to, if you don't mind, change that to X. So it'd be X cubed cosine 4X. Is that the one? Yeah. Okay. So, what kind of rule are we looking at here? We're looking at product rule first of all. And the product rule says derivative of the first, leave the cosine 4X alone, plus X cubed left alone, times derivative of that. Now, we were having a conversation in here this noon, and I want to make sure I'm very clear on this. When we had a 4x 2 weeks ago, we said kick out a 4, right? Well, you don't usually hear me say kick out a 4 anymore. What are we doing? It's chain rule. It's derivative of the inside, isn't it? So I guess what I don't want you to do is do both of those. I don't want you to kick out a 4 and then do the derivative inside, right? And then you have 2 4s, and that would be no good. So when we said before kick out a 4, what we were doing was the derivative of the inside. Okay. So the derivative of cosine is negative. I think you should stick that back here in front. We're going to have sine 4x, and then we're going to multiply by a 4. Now, and here's a negative, right? Because the derivative of cosine was negative. Now, that 4 could go around front, but I don't think it has to. Let's do it. I mean, get the habit. Am I going to count off? I don't know. But just pretend like I'm good. Pretend like I'm good. How about that? Well, here's what I've been saying. Okay, this goes back to what Rick said, combining things. Well, to me, you got a 2 times a 3, you better multiply. So if this is a negative 2 here and a 4, definitely. If this was a negative 2 here and this 4 was sitting here, then you better make negative 8 out of that. So to be honest, this is a negative 1 sitting here, right? So a negative 1 times a 4, I think you should do that. Get negative 4. Now, if this was a plus, I guess here's why I said I don't know. If this was a positive right here, then I don't think putting the 4 out in front really combines anything. I think it just rearranges it. It takes a 4 from the end and puts it at the beginning. But here, I think putting the 4 in front is important because it combines the 4 with the negative 1. Does that make sense? That's why I thought that's something you should do. So I think this should be a negative 4 out in front when you're done right. Because to me, you are combining 2 numbers there. You're putting negative 1 times 4. But other than that, that's it. I mean, you can't really do anything. You can take out an x squared. But again, you don't do anything with it when you take it out. So don't worry about it. But it's good that you see it's there. Because if this was a quotient rule and there were some x's on the bottom, then taking out the x squared would be good.
Would you kind of run quickly negative 4 times sine of 4x, or sine of 4x, and then just have x cubed afterwards?
That would be just the rearranging, and so that I don't care about. Okay? All right. What else? Brittany, were you going to ask that one? You going to ask that one? 17. Okay? So we have y equals e to the r squared sine r. Is that the one? Okay? So what rule are we doing here? Well, not at first. It is a product rule. Yeah. First of all, and not that it's that important, I'm not going to ask you that or anything, but first and foremost, this is an e to something derivative. So e to some stuff is e to the stuff times the derivative of that inside stuff. It just turns out that the inside stuff this time is a product rule. So the derivative is going to be e to this stuff left alone, that's the inside, so we're leaving the inside alone, times the derivative of the inside stuff, so big set of parentheses, and that's going to need a product rule. So the derivative of this as a product rule would be 2r times sine of r plus r squared cosine r. And there's absolutely nothing else that needs to be done. And so this is what I mean by there will be a number of problems, probably half of them, that where you do that, you're done. I mean, really, there's just not going to be. We've been kind of focusing on the ones where you could factor something out or you could combine some things, but there just isn't anything to do there. I mean, I could factor out an R, which would be okay, but doesn't really need it. 36. Yeah. Read that to me. Is it log base 10?
Yeah, log base 10 of x, all 20 cubed. And that's all.
Okay. This would be on the hard side of things just because it's a quotient rule, which makes it a little more complex anyway, just kind of messier. And it's got an inside piece that you're going to have to deal with, you know. So this would, but I don't think it's terrible. And when you mix these log and tangent stuff like that, a lot of times there ends up nothing can simplify too. We talk about e to the x because there'd be a couple of them you could factor out, that kind of thing. So we start with derivative top, which is inside left alone to the second. That's easy to forget. Okay, so there's a derivative outside. Leave the inside alone times. No. We still have to do the derivative of the inside here, which is messy enough just on its own. That's 1 over, 1 over x times 1 over ln 10. Okay, so let's back up here. So the rule of a log of another base is 1 over the inside stuff, so that's the 1 over x. Then 1 over ln of the base, so 1 over ln 10, and then the derivative inside. Of course, the derivative inside now is just x, so the derivative that's just 1. So we're good. So all of that was just the derivative of the top times bottom left alone minus top left alone times the derivative of tangent, which you just have to memorize. Derivative of tangent is secant squared. All over, sometimes people forget this part because they did so much, you did spend so much time doing all that, you forget it's a quotient rule. Tangent squared, which you can write with our shortcut notation, that's fine, just understand what it means. So then the big question is, what can you do with this? Hopefully the answer is nothing. You could okay, because what do you got here? Again, on your quotient rule, remember, because of that minus, you know, the ho-de high minus high-de-ho, the ho-de high is one thing, minus the high-de-ho. With a quotient rule, you always have two kind of terms. You have two things that are a bunch of things multiplied together. Okay, so you got that minus that. So when you're factoring out, it's like, man, it's saying we could factor out a log base 10 of x all squared. But there isn't anything down here to cancel. If there was a log base 10 of x down here, that'd be great. Let's do it and cancel. Since it's not, I'd say don't even do it. And can any of these things multiply together? Not really. I mean, you do have, like that first one we did today, this is over 1, this over, these are on the bottom. So I could take this first red thing and make a kind of a fraction out of it. I could have a 3 and a log squared and a tangent on top of an x and an ln 10 as a fraction, minus that. But that's just kind of rearranging. So I don't care about it. So really, you're done. So it's not uncommon in a quotient rule, even a messy one, to get to there and have a bunch of stuff that looks like that and not really be able to do it. Yeah, I mean, which is good. Okay? Yes? Hey, there's that thing we saw with that ln. If you, like Sam was saying earlier, we could split this apart, this red one over that, and this red one over that, and then this tangent would cancel with one of those tangents, yes. But we don't have to. Okay? All right, good one. What else? Let's. Why don't we go to the website and throw a few of them up there and let everybody practice them? Okay. and then we can still hit some of these same questions as we go along. All right, so if you go to Kearney High, KearneyCats.com, and you find, to our classroom. Hopefully many of you have been there. If you've never been there, either you never miss or I don't know, but that's fine. But here's where it is. In the link section where our class videos are, in the link section where the class videos are, there's derivative practice 1 and derivative practice 2. Now, some of you are asking about the derivative rules. They're way down here in the files section. It says derivative rules. Okay? And so you click on that, and it's just a PDF that opens up. Okay? And it's that derivative rule page if you want to look at it. Okay? And so anyway, if we go to derivative practice 1, it takes us to this page right here. Now, I think this is a good one for us to do in class because I'll skip over the ones that aren't really that useful. When you're doing it at home, you might not know which ones to skip over and which ones not. And then, so this one might not be the best one for you to use at home. But I think we could do a few off of here. So let me go, let's go through here. Let's start. Now, I'm on difficulty 2. I've got all the boxes checked, which involves, except for this bottom row, which we won't have to do any of those. Okay? So we'll start with difficulty 2, and we'll try to pick out a couple here. There you go. Here's one right here. It says 9. Yes. The second one does. This one does not, but the second one has some implicit, and we'll get to those. Okay, we are going to do some of those. And this one, and they both have some arc sine, arc cosine practice. Okay, this is 9 ln x times square root of x. Go ahead and try that one. 9 ln of x times square root of x. All right, ready to see it? I've got 9x to the negative 1/2. Because what happened there? Oh, the problem's not up there anymore. Oh, here it is. So when you do the derivative of the first thing, you get 9 times 1 over x times x to the 1/2 left alone. You can put those together, right? 1 over x. So if you've got 9 times 1 over x times x to the 1/2, those right there reduce or cancel or however you want to do it. In other words, this is 9 times x to the negative 1 times x to the 1/2. You can add those powers together. And that's 9x to the negative 1/2. So that's something you should do. That's some simplifying you should do. Or you could treat it as x to 1/2 over x, and you can subtract those powers. So 1/2 take away 1 is negative 1/2. Okay? So I wrote it 9x to the negative 1/2. Now you could have it 9 over x to the 1/2. That's the same thing. And then plus, and then the 9 ln x left alone, but then we do the derivative of x to the 1/2, you bring the 1/2 down in front. Well, the 1/2 times the 9, you should do that, and that's where the 9/2 comes from. ln x is left alone, and then the x to the negative 1/2. Yes?
So we're going to factor out the 9 prior to combining the 1/2 in front of the x, we did the derivative of square root of x.
No. So if you had a 9 out in front, and then you had x to the negative 1/2 plus 1/2.
Yeah, but I guess you have 9 over 2, and that's when you combine the terms for the second portion.
Right.
And I was asking if you had factored it out prior to combining them, would it have been?
Right. Right. So your final answer would have had a 9 out in front, and then, and you can even do it now. But yes, it's okay to do that. Okay. All right. Let's find another one. Okay, I've kind of got a certain one in mind here. Let me just skipped. There we go. 8 arc sine of x. 8 arc sine of x plus square root of x. 8 arc sine of x plus square root of x. That should have been pretty easy, really. I just wanted to do arc sine. So the 8 would be on top. You wouldn't have to have it on top. You could have 8 times. What's this? 1 minus x squared. Is that arc sine? Plus 1/2 x to the negative 1/2. Right? I mean, there really isn't anything else to do. I mean, that would probably go under the easy category. It's pretty straightforward. Not anything on the inside, nothing like that. I suppose the only thing that might make it medium is you had to remember arc sine. You know, it's not one of those we run into every day, so you got to make sure you remember it. But to me, knowing all the rules should be a bare minimum. If you know, so if you know all the rules, that's an easy one. Okay. Let's bump up to 3 difficulty. E. There's a good one. 7x to the negative 2, whoops. 7x to the negative 2 minus 4 raised to the arc cosine x. That A cosine means arc cosine. So 7x to the negative 2 minus 4 raised to the arc cosine x. All right. Here's what I got so far. Any problems with that? Where'd the ln4 come from? Where'd the ln4 come from? We have 4 raised to a power. The rule for 4 raised to a power is this rule right here. 4 raised to some stuff is 4 raised to that same stuff times ln4 times the derivative of the inside stuff. So it's just knowing that particular rule. Oops. So that is where the ln4 came from. So this one's easy here. This is 4 raised to some stuff, so leave that alone, times the ln4, and then times the derivative of the inside stuff, which is our cosine. So the derivative of our cosine is -1 over all this. Now there is one more thing I can do. I could put this stuff on top of this stuff, because what we have here is one term here, minus, and then a whole bunch of terms here. But it's minus a negative. Because that's like a -1 in front of this 4. The 4 is not negative, okay? Make sure you all understand that. The 4 there is not negative. It's minus 4 to the, what that is a -1 times 4 to the x. So very important. If the negative is, if the base is negative in an exponential, then it's got to be this, right? There'd have to be parentheses in. So when you have -4 to the x, that negative is really a -1 times 4 to the x. So that -1 would be times that -1 up there, make it positive. So I would want you to do that, especially on the first one. If you're taking the second one, I'm a little pickier on the first one. If you're going to get 30 out of 30, it's going to have to be pretty good, right? I mean, you already get a miss 2 and still get 30 out of 30, right? So I'd be a little pickier on that one. Now, if it's the second or third one, and that alone was going to keep you from getting 8 out of 10, then I might let that go. Okay? But anyway, hopefully you don't even get to that point. All right, let me take off a couple of these. Let's take off that log. Let's take off the inverse trig because we've done a few of those. Let's see what we do. There we go. 8 e to the x. Try not to look at your rules if you don't have to. 8 e to the x minus 7 cotangent x plus secant x.
Can you go to the page? Is that a question? Why are these two different? Or how?
These two?
Yeah.
This is E as the base.
Oh.
And these are all any
like
other
numbers?
base. 2, 3, 4, 7, whatever. These are just numbers. So the difference is when it's just a number,
Then
it's
you
not
have to
E.
add that.
You have to tack that.
Okay.
And the same thing with natural log. Natural log is just that. But if it's a log with a different base, then you have to tack that.
Is that
Otherwise
on
it was-
the website?
Uh-huh. All right. something like that. Now, if you know your rules, this is an easy one. I mean, there's no chain rule, there's no product rule, there's no quotient rule. I mean, it's just the rules, right? I mean, so to me, that's by definition what the easy ones are. They're just, maybe a little bit of a power rule or just pretty much knowing the rules on the page. Okay, and not having to do some messy stuff like product quotient, but just the basic functions. Derivative of cotangent is negative cosecant squared. So that's why it turns into a plus here. And derivative of secant x is secant x times tangent x. Okay? All right. Let's go to the next web page. So on the Kearney High website, you got derivative practice 1. That was that one. That's a little harder to do at home because, notice I was on difficulty 2 and 3. I had most of them checked. Some of those are good. Some of them I don't think are as good. But so that's a little harder to do. Derivative practice 2 is a little easier to use at home. Derivative practice 2 is from Arizona State. This is their derivative test for their Calc 1 class, or it was in 2003 anyway. Practice test, and this got the test with the answers. They're not all worked out, but they just have the answer. And then test 2 and test 3. They get a little harder as you go along. And then they have the actual test from that year with its solutions. Okay, so if you go to test 1, it's just a PDF document, which you could print out. Or you could just scroll and work on your own. Okay, so if we scroll along here, you can see pretty easy. I mean, it starts out. I mean, again, just your basic rules. Let's do number 2. I mean, it should be pretty easy, but stuff like that I put on, I think they're easy, and then all of a sudden we screw it up. So let's just see what you do with that. So x squared over 3 minus 3 over x squared. That's the function. All right? Don't look if you don't want to see it yet. To me, the danger on both of those terms is that you think of the quotient rule. And that's just, you could get there. They'd be the same eventually, but there's so many places you could screw it up that it's just terrible to do it that way. X squared over 3, you should always think of as 1/3 x squared. And that makes it much easier. Just bring 2 down in front. You got 2/3 x to the first. And then 3x to the negative 2, bring negative 2 down, makes plus. So there you go. So to me, again, that's an easy one, but you got to rewrite it first. Now, you look at number 3 here. You wouldn't want to do a product rule on that. You'd want to distribute those things first, then do the derivative. Here would be a quotient rule 1 that you'd probably do as a quotient rule. Here would be another one that you probably would do as a quotient rule, although you could split this one apart. Actually, probably be smarter. Okay, so I don't know, we wouldn't have a lot of that, but there'd be one. This would be one that is probably about, well, it's probably still easier if you split that apart, but quotient rule wouldn't be horrible. Quotient rule you pretty much have to do on this one. So the reason they give you those two is kind of show you the difference. This one, pretty much have to do a quotient rule. There's no canceling you can do. So these are pretty straightforward with some algebra. That's probably a quotient rule. That's very much like the one we just did, number 10, except it's got some square roots in it. Okay, another quotient rule 1. Here'd be one I'd FOIL out first and then do it. Here'd be a pretty straight power rule kind of thing. Let's do this one, number 16. Again, it should be an easy one. 6x to the negative 3 halves plus 7x to the 1/5 plus 1. The answer's up there when you're ready to look. Okay, so again, I think a pretty easy one, but it does have those fractions in there. Remember, when you multiply fractions, you can just take 6 over 1, negative 3 over 2, and you can just multiply across. So that's negative 18 over 2, which is negative 9. Or you can cancel the 2 with the 3, whatever. Okay, so I see people try to get common denominators or whatever. Not when you're multiplying fractions. You don't do that. Okay, I think that's pretty much it on that one. Again, there's some other ones you could do. But let's back up. That was test 1. So test 2 gets a little trickier. Now we start getting into some more chain rule. So let's do one of those. Do number 3 here. Do number 3. Okay, answer's up there if you want to look. Again, there would be some things you could factor. It's two quantities added together. You could factor out some of those common quantities, but it doesn't really do much for you, so probably not necessary. Definitely not necessary. But it would be, if this was, but clearly if this was a stationary point problem and we want to do the derivative equals 0, then getting it into factored form would clearly be what we would want to do. So we would definitely want to be factoring some things out because that would lead us to our next step. But for right now, that's okay. Yes?
If you worry about the 2 on the inside of e, that e to the 2x minus 1.
That's where this 2 came from.
Oh, I didn't see
Derivative inside.
it. Oh.
That's what we talked about earlier, that kick out. When I looked at this, again, after lots of practice, that's what I noticed. The inside, oh, it's just derivative of the inside just 2. Here, the derivative of this inside is just 3. So that's back to the first thing we learned where we just kick it out, but that's really chain rule. So when I was doing this derivative, I said, oh, yeah, I'll be that with the 2 out. Then that by 1. And then there'll be this, and I know I'll bring the 3 down in front, and I'll be kicking out a 3. So, you know, you could have done that without even that intermediate step. But there it is. Okay, so let's go on here. I got a couple others I want to get to. I want to get to a implicit or 2. Oops. We've done some quotient rule already. Ah, there we go. That's what I want to do. Okay, let's do that one, and then we'll get to implicit. Don't forget that cubed is really on the outside, right? Cosine cubed, it's really on the outside. That is the key to this problem. The whole reason I picked it. Okay, what kind of things, some of you are just finished up, I know, but what kind of things do you end up combining then in your final answer? Aren't there some things that combine there? What are they? There's a and a negative. So wouldn't there end up being a negative 3/2 out in front of all of it? That's what I'm showing. Okay, because first of all, I've got this. This is all cosine x to 1/2 all to the 3rd power. That's the key first phase to just rewrite it so it looks like that. Now when you do your outer, you bring the 3 down in front. Then this would be squared. You would leave the cosine root x alone. Then you do the inside, so big parentheses. Derivative of cosine root x is negative sine root x. Leave its inside alone. Tack on then the derivative of its inside, which is 1/2 x to the negative 1/2. When you look at that, that big parenthesis I put there isn't really necessary. It's just this times that, times that. So the 1/2, the negative, and the 3 can all come out in front. And to be honest, the x and the negative 1/2 probably should have pulled that along too in front. But that's just rearranging, so I don't care about that. Okay, so it's that cosine squared, and it's that sine, and then it's that. Yes, please. This cube is, yes. Anytime you see sine squared, cosine squared, whatever, it's just lazy shortcut notation. That 3 is really all of this cube. Absolutely. So whenever you see that sine cube, cosine cube, it's outside of that whole cosine function. Okay? And they'll probably be on there because that's pretty normal notation, and we see that a lot. So I'll probably give you one like that. I don't know if it'd be on the first one, it could be on the second one, or whatever. You'll probably see one that looks like that because that's just notation we commonly run into. So we got to be able to handle it. It's not really nice for us when we're wanting to do derivative, but it's kind of convenient other times. All right, so that was worksheet 2. So worksheet 1 was kind of the basic rules, nothing too fancy. Worksheet, it had some products, some quotient in it. Worksheet 2 got into more chain rule kinds of stuff, so it's certainly a good one to practice. And then worksheet 3 is when we get into just the arc signs, so you're going to get into those. Here you get 10 to something, so that's what we tack on. That's what Riley you asked about. That's where you tack on the ln 10, right? That gets into some more. There's an arc cosine right there. It gets into some logs, I think, of some other bases. So this worksheet gets into, there's a 5 to the x right there. Okay, here we go. Here is an implicit differentiation right here. Let's do that one. Now you know right away it's different because it's a mixture of x's and y's. It doesn't just say y equals. Now you could have an implicit that says y equals, but the other side would have x's and y's in it. Okay, it would have a combination instead of just y equals and then x's. Okay, so let's do number 9, and there's another one we can do if we get time here. Remember, the basic idea is do the normal derivatives, but the ones that have the y in them, you tack on a y prime after you do the normal derivative. Okay, so that's my first step on that one. Remember, the derivative of x squared is 2x, but if it's y squared, it's 2y, y prime. The derivative of 2x is 2. The derivative of 2y would be 2 with a y prime. And this is the one we mess up a lot. 2y, we want to do 2y, y prime. No, the derivative of 2y is just like 2x. It's just 2, then the y prime. Sine y, the derivative is cosine y, and then tack on a y prime. Okay, now what do I do? Gather the y primes on one side. So that would be those two terms. Get those to the left. Leave the 2x there on the right. Then what? Factor out a y prime, which leaves you 2 minus cosine y equals 2x. And the last step, divide. 2x all over 2 minus cosine y. And your final answer will probably have a mixture of x's and y's in it. That's normal. That's normal. Okay? That's implicit differentiation.
Were there questions on the Gabor test asked the differentiate between asking for something for y directly or explicitly as it is
And that one homework, no. It'll be 10 questions. Most of them will be, it will look just like this. Y equals, y equals, y equals, y equals. And then all of a sudden you'll run into one like this. And you'll say, hey, that's implicit differentiation. But, you won't have that option. Hey, do it like the homework. No. So that's just find the y prime. Okay, now, if we scroll down here, there's some more down here. I wanted to comment on, see, these are just normal ones now. There's another one, just like the one we just did. Okay, an implicit one. There's a regular one that's just got x's in it. And that's just got x in it. That's a mixture of x's and y's, but that'd be a product rule with cosines. I mean, that'd be possible. That'd be a quotient rule, which I'm not going to give you a quotient rule on. Here's what they'll usually look like, something like this. And we're going to run out of time here a little bit, so we'll just maybe walk through this one together. What do you got to do right there? That is a product rule. That is a product rule right there. So let's together just write what that would be. 2x y cubed plus x squared. Now, okay, 3y squared. Do not leave that 3 in the middle of that. Okay, like when if you have 3ab, you don't write it a3b, right? We put the 3 out in front. So when you're done, or right here, or whatever, Get that 3 in front of that term like that, where it belongs. Okay, plus 6y, y prime, right? The normal derivative of 3y squared would be 6y with a y prime. Equals 1 minus derivative of 4y is 4, and then tack on the y prime. So you'd have 1, 2, 3 terms that have y prime in it. So they all need to get together. So those two are already on the left side, so swing that one over, move that one to the other side. Okay, and then go about your business of factoring out the y prime and going from there. So those are good. I want to make one more comment about this. Implicit differentiation. 2 common mistakes that I see people make. For some reason, most of you knew, which is great, that this was a product rule. For some reason, if I give you one that just has xy, people forget about the product rule. That's still a product rule, xy. So it'd be 1y plus x y prime, right? It's still a product rule. And if there's a negative, if this is a subtract sign here, stick that negative with that x so it stays with it. Okay, that's first thing. Then I sometimes see people do this. So I give you this problem here, and this got 7 on this side. When you do the derivative of that, what do you get? 0. So I see people do everything beautifully, and then all of a sudden they get over here and they put a 7. They keep a 7 there instead of a 0. You're doing the derivative of both sides. So the derivative of 7 is 0, so make sure you do that. Okay, so that's test 3, and then if you go back a page, it's got their actual test. It's about 15 questions. I think their test was 15 questions, which is a mixture, and you could look at those. So page 195, still a good thing to practice, but I know I know of some people who have done all those already, and that's great. I mean, if you've done that many, you should be in pretty good shape. But so this would be a good place to go next, especially these, the Arizona State ones. That's derivative number 2 practice. Okay? And then those of you, if you don't make it, you're going to have to take it again. Remember, we're not going to spend class time on that. We're going to move on and be doing some other things on Wednesday and Thursday. I mean, this is it. This is the last we'll spend of class time doing derivative practice. So after that, it's kind of on your own.